All right, everyone, let's continue our discussion with inference. Remember that last time we talked about point estimators and we saw that the base of reliance on point estimators is law of large numbers, and then we moved on. Developing intuition based on central limit theorem, and central limit theorem, roughly speaking, says x bar has a roughly speaking distribution of x bar regardless of underlying population distribution is normal, all right, for of course big enough sample size. So one concept that I want to iterate this concept, z of alpha over 2. This one is a point on x-axis, that area after that point is alpha over 2, and it says z, so this is the area under the curve after that point under the curve of z distribution or standard normal distribution. All right, for example, if this is curve of standard normal, z of alpha over 2 is going to be the point on x-axis. The area after that is area under the curve after that point is alpha over 2. Well, this is symmetric, right? Symmetric around 0. Then area before minus z of alpha over 2 is also going to be alpha over 2. Well, why did I use minus z of alpha over 2? Because this is symmetric around 0. So if, for example, z of alpha over 2 is 2, there is an equivalent point at the other side of 0, minus 2. That area up to minus 2 is alpha over 2. So area after 2 is going to be alpha over 2. All right, so the very basic concept to keep in mind. Here is how we can find z of alpha over 2. Moving forward, it is going to be equal to norm.s.inv of 1 minus alpha over 2. Well, why did I use 1 minus alpha over 2? Because norm.s.inv accepts area up to that point, all right? Area up to that point is 1 minus alpha over 2 because area after that point is alpha over 2, all right? Now, let's talk a little bit about shortcomings of point estimators. This is if your unknown parameter of population is mu, and you take samples, these are x bars from different samples, all right? X bar could be like x bar 1 and x bar 2 that are close to mu. Again, we don't know value of mu, right? Close to mu, so they are good. If we use x bar and x bar 1 and x bar 2 to estimate mu, then we are in good shape. But what if you take a sample and this is completely possible? What if you get x bar 3? Well, if I get x bar 3, I'm going to be way off estimating, using x bar 3 for estimating mu. Or if I use x bar 4, that's even worse, all right? This is where the concept of confidence interval comes into play. It's an interval, it's a random interval, all right, that we are going to say it's a random, so we are going to define probability for it. We are going to say this interval contains unknown yet fixed parameter of mu with certain probability. All right, so then we, instead of just relying on one point estimator, we are going to give an interval saying, you know what, that unknown parameter that you are interested in is going to be in this interval, and this interval, in other words, contains it with a very high probability of 95 or 99%. Moving forward, we are going to see how we can build this confidence interval. Well, this is an interval, so it is going to have a lower limit and it is going to have a upper limit. Lower limit, we are going to show that with LL, upper limit with UL. I'm going to go over this proof one time, but I'm going over this so that you are familiar with how we come up with confidence intervals. This is just one time we are going to go over this, and then we are going to be done. So it's actually pretty straightforward, the way we come up with confidence intervals. So the idea is right here. Idea comes from the concept of z of alpha over 2, as a matter of fact. We know that under z distribution, if this side is alpha over 2, this side is alpha over 2, area in the middle is 1 minus alpha, right? Because this is alpha over 2 together is alpha. Area between those two is 1 minus alpha, right? And that's exactly what we are going to do. We are going to say, we know that x bar minus mu over sigma over square root of n is going to be between z of alpha over 2 and minus z of alpha over 2 with probability of 1 minus alpha, right? Then let's move things around. What do I mean by that? Multiply by sigma over square root of n, sigma over square root of n multiply, then multiply one time by minus 1 and add x bar to it. You are going to come up with this, finally, this equation. See, this is exactly what I have. Probability that x bar minus z of alpha over 2 times sigma over square root of n all the way to x bar plus z of alpha over 2 sigma over square root of n. In the probability that this interval contains a value of mu is equal to 1 minus alpha. There you go. You have your confidence interval for mu. So it is x bar minus z of alpha over 2 sigma over square root of n all the way to z of alpha over 2 x bar plus z of alpha over 2 sigma over square root of n. So we say this interval contains unknown yet fixed value of parameter mu with what probability? Well, the value of probability is right there, 1 minus alpha, right? For example, for 95%, let's build a confidence interval. Well, for 95%, 1 minus alpha is 95%. So your alpha is 5%. Alpha over 2 is a 0.025. So all you need to do is just plug in z of alpha over 2 right here. You have a value of sigma, you have value of n, you have value of x bar, done. You have the confidence interval, all right? So let me actually finish with this one right here. Let's say I want to build a confidence interval for mu of normal population when I know sigma. So sigma is known. That confidence interval is going to be x bar plus minus z of alpha over 2 sigma over square root of n. That term right there, z of alpha over 2 sigma over square root of n, we call that margin of error. That right there is margin of error. Lower limit is x bar minus z alpha over 2 sigma over square root of n, and that is your upper limit right there. So this is a 1 minus alpha 100% confidence at the level of 1 minus alpha 100%. All right. I'm going to pause here and record another one. This is a practice problem for you. Go ahead and try to solve it. We will solve it in class together.